Okay, I've decided to give you folks some more homework help. So this will help you with assignment 41. I'm not going to do, well, I'm not going to say that completely, but I'm not going to do the textbook problems that I have assigned to you from assignment 41. But I will do numbers 22 and 29, which are similar to a couple you have to do. And if you stay tuned, or I suppose fast forward, I will do other problems number 1 and 2 for you. How does that sound? So I'm going to give you a little bit of help here. In other words, if you watch carefully and stay tuned, you'll find the answers to those two, and I'll even show you how to do it. So a little bit of extra help for bearing with me so far during this flipped video experiment. So here we go. Let's take a look at page 427, number 22. It says you have 26.42 grams of ammonium sulfate, and that's dissolved in 50.00 milliliters of solution. Part A says, what is the formula weight of ammonium sulfate? We can do that pretty quickly, can't we? Let's see. We have got 2 nitrogens, and each nitrogen is 14.01, so wouldn't that be 28.02 from the nitrogens? And we've got a total of 8 hydrogens. Each one of those is 1.01, so isn't that 8.08 from the hydrogens? And let's see, we have sulfur, 32.07. And we've got 4 oxygens, each one 16.00. That would be 64.00 from the oxygens. If I did my math right, 132.17 grams per mole. I'm going to cheat and look at the answer key in the book. Oh, they say 132.1. I disagree. I think it's closer to 132.2. All right, next up we have to find the molarity. Now we know molarity is moles of solute per liter of solution. So we have 26.42 grams of solute. And of course we know that is ammonium sulfate. So we need to get moles on top. So I'm going to go from grams to moles of ammonium sulfate. And 1 mole we just figured out was 132.17 grams. So that's moles divided by liters of solution. Now that's milliliters, so in liter land, that would be 0.0500 liters. So the unit I have left, oops, hope you guys could see that. The unit I have left is moles per liter, which is exactly what I'd like. Looks like we're allowed 4 significant figures, so 26.42 divided by 132.17 divided by 0.05000 to 4 significant figures would be 3.998. And the capital letter M is the symbol for molarity. Okay, that wasn't too bad. Let's do number 29. Number 29 says, how many kilograms of water would be needed to have 75.5 grams of calcium nitrate form a 0.500 molal solution? Now molality is moles of solute per kilogram of water. Now this is the part we want down here. Now for this, kiddos, I like to start with moles of solute. My problem is I have grams. So we get to do one of our favorite things. We're going to take 75.5 grams of calcium nitrate, and our first step will be to convert that into moles of calcium nitrate. Let's figure out what that formula weight is. Calcium is 40.01. Sorry, I lied. 40.08. Plus, we have 2 nitrogens. Each one of those is 14.02, so that's 28.02. And we have 6 oxygens. Each one is 16.00, so that's 96.00. I get 164.10 grams per mole. Okay, now that gives us moles of solute. We do not want that. We want kilograms of water. So as I showed you in your notes, we're going to use our molality as a conversion factor. We're going to put moles of solute on the bottom and kilograms of water on top. Now, doesn't my molality say 0.500 moles per kilogram of water? So I'm going to put 0.500 moles per kilogram of water. And we're just going to use that as a conversion factor. So let's see what we end up with. We'll clear this out. 75.5 divided by 164.10 divided by 0.500 to three significant figures is 0.920 kilograms of water would be needed to form that solution. Okay? Alrighty, as I said, I was going to help you out with other problems number 1 and 2. Do me a favor, don't tell the other kids that I'm doing this for you. Let it be a reward for them. If they watch the videos online, they might get a little surprise. Okay? So number 1 says how many grams of sodium sulfate? Now sodium sulfate is Na2SO4. Sodium's 1 positive and sulfate's 2 negative. So we want to know how many grams of this stuff we need. If there are 350 milliliters in a 0.250 molar solution. Now for this problem, we're going to go ahead and start with our volume in liters. So 0.3500 liters. Then I'm going to use my molarity as a conversion factor. I'm going to put liters on the bottom and get into moles. So it's Na2SO4. The molarity is 0.250 moles per liter. So you see how liters divide out when I use that as a conversion factor? And then my last step is simply to go from moles of Na2SO4 to grams. So we have to figure out the formula weight of Na2SO4. That shouldn't be so hard. Sodium is 22.9, we'll say 22.99 grams per mole. And there's 2 of them. Plus sulfur is 32.07. Oh, I messed up there. Let me try that again. So let's start with our sodiums again. 22.99 times 2 plus 32.07 for my sulfur. And each oxygen weighs 16, and there's 4 of them, so that's 64. I get 142.05 grams per mole. So you can see moles divide out and I have grams. So 0.3500 times 0.250 times 142.05. Now I'm only allowed 3 significant figures, so I get 24 grams, or 12.4 grams. Now if you look at my answer key, this answer is given. Now remember why I do that? I give you the answer so you can tell right away whether or not you've done something wrong. And if you do it wrong, you can go back and check your work. Sometimes it's as simple as getting the formula weight wrong. At any rate, you must show your work for these. Alrighty, let's take a look at other problem number 2. So we have other number 2. This time, I want to know what volume of a 0.75 molar solution can be prepared from 500.0 grams of potassium carbonate. Potassium carbonate is K2CO3. Remember, potassium's +1, carbonate's 2 negative. So for these, I like to start with grams, and I need to get that into moles. So K2CO3, we are going to go from grams to moles of K2CO3. So let's figure the formula weight of that out. Potassium is 39.10 plus carbon. Oh, we have 2 potassium, sorry, so let's times 2. We have a carbon, which is 12.01 plus 3 oxygens, which are 16.00 apiece. So I get 60.01 grams per mole. So grams of potassium carbonate are gone. Now I'm not finished because I want to know what volume. So I'm going to use my molarity again as a conversion factor. But this time I'm going to put moles of K2CO3 on the bottom and liters on the top. And my molarity is 0.75 moles per liter. Isn't that what that says? 0.75 molar? 0.75 moles per liter. So moles divide out, and I'm left with liters. So let's see what this turns out to be. 500 divided by 60.01 divided by 0.75. We're only allowed 2 sig figs, and I get 11.1 liters. Now my answer key says it should be 4.8 liters. So let's see what I did wrong this time. This is a great way to do this. First, let's check our math. I have 500 divided by 60.01 divided by 0.75. Nope, I still get 11.1, so it wasn't my math. I wonder if it's my formula weight. That looks suspicious to me. Doesn't it look suspicious to you? Let's check it again. There's 2 potassiums. Now each potassium, kiddos, is 39.1, and there are 2 of them. Interesting. 2 potassiums alone weigh 78.2. So my formula weight was what was wrong. Let's go ahead and finish this out. Plus 12.01 for my carbons and 48 for my oxygens. So 138.21 is my formula weight. Now let's try the calculation again. 500 divided by 138.21 divided by 0.75 equals, I'll be darned, 4.8 liters. Okay, so now I did that on purpose. Maybe you guys noticed as I was going through it the first time and said, whoa, you made a mistake. And you were patient. Did you see how I sort of figured out where my mistake was? I first checked my math, then I checked my formula weight. Now if that wasn't the problem, then I may have checked my molarity. Maybe I copied that number wrong, or sometimes those 2 guys are flipped over. Alrighty? So let that be a lesson to you. I hope you enjoyed it. Bye-bye.